Today we're talking a little bit about logic. We've already broached the subject in our previous video on sets. This is a well-known painting by the famous French artist René Magritte. The painting is entitled La Trahison des Images, meaning the treachery of images. And the inscription on the painting, written in cursive, declares that this is not a pipe. Which of course is correct. This is only a picture of a pipe. Just like this is not Italy. It is only a map of Italy. Our everyday language, of course, tends to be lax about such distinctions, but one of the points we face in this video is the need for recognizing and preserving these distinctions. My friend Larry emailed me to say he was having trouble with some of his Perl code. I told him if he sent me a copy, I would take a look at it. When my eye fell on this small segment of his program, I could see at least one problem that he probably had. I emailed him back and told him, Larry, try putting a space between the W and the $sign. A few minutes later, Larry responded telling me that the code still didn't work. Larry, I said, I don't believe you. Send me another copy of the code after you fixed it. And this is apparently how he interpreted what I had told him to do. So look at this and have a laugh at Larry's expense. So, I wondered to myself, how could I clarify my intentions in an email message? Maybe there's some other way I could try to specify a blank character. I remember seeing a B with a slash through it that was used for this purpose in some textbooks I've seen. Unfortunately, I cannot find such a character on my keyboard. It doesn't seem to be available in my email text editor. So, in plain English, I decide to just tell Larry to put a space there. Fortunately, he gets the point, and after fixing his code, the program runs. The point here is the need to distinguish the meta-language of our communication from the Perl language that is the object of our discussion. When we discuss formal logic, this inevitably requires some care. Hold that thought, and now let's move to the subject at hand. We're trying to do analysis. Here's a typical kind of statement that we might see in real analysis. This example says that between any two distinct numbers, another number can be found. Here is a paraphrase of that statement. Same thing. If A is less than B, then there exists a number C such that A is less than C is less than B. Does that mean the same thing? Probably, at least in the real numbers. Hopefully you recognize that these are two statements saying the same thing, and in fact, in the real number system, they are true. Here is a formal string of symbols which has more or less the same interpretation. For all A and B, if A is less than B, then there exists a C such that A is less than C and C is less than B. Now the difference between this formal string of symbols is it's really to be treated like a picture of the statement, as distinct from the reality. Is a picture of the statement in either of the two forms I've shown you above. So it would be very much like taking one of the statements above and just putting quotation marks around it. That's like saying treat it as symbols rather than a meaningful statement. So let's spend a moment talking about that distinction, but also I want to talk about some of the other logical features of this, and that's why these symbols are important to highlight the logical structure. In this case especially, I want to talk about the quantifiers. In particular, we want to point out two kinds of quantifiers that appear in this statement. The first is what we call a universal quantifier. In the first sentence, it's expressed by the word any. Other words used to express universal quantification, to quantify universally, are words like all and every. In the second statement, there is no explicit word used for a universal quantifier, but it is implied. When we say if A is less than B, what we really mean is for all A and B if A is less than B. It's implied. When we're supposed to understand something like this, then you just have to take it from context. Now, in the third version, we have an upside-down A that is used to express universal quantification. Now look at the existential quantifier, which in the first sentence is written as can be found. In the second version, we have there exists. Other popular words used would be there is. In the third version, the backwards E is used. Now, these three ways of writing the same thing may look identical to you, but I want to point out the important difference that has to do with the third version with the logical symbols. First, let me point out, if you really did want to go beyond calling the third sentence a picture and want to give it some semantic meaning, then this is how you would write it. If you want to go beyond a string of symbols and say that something is actually a fact or is true, you could say it's true in the reals, it's true in the rationals, and, well, true in the integers? No. So you put a slash through that. Now, I'm not even going to ask about for the complex numbers because there the sentence would be just meaningless since we don't have an interpretation for the less than sign. So if I call our statement phi is a statement, but it's a symbolic statement. I've shown you how to say that phi is true in the reals and in the rationals, but not in the integers. The distinction I want to point out is the first two sentences on top have a semantic meaning in our English language, which is a meta-language for the mathematical language, making an actual assertion that something is true. The third version is just something for you to look at and analyze. So the distinction between the semantic and the symbolic or formal is what we're looking at here. The symbols appearing in phi are just symbols without any meaning. Until we say something like what we have at the bottom here, or we say that the real number system satisfies phi, we haven't actually made a meaningful assertion. The first and second version at the top of the slide are statements which are true in the reals and the rationals, false in the integers. The symbolic version phi is neither true nor false, it's just a string of symbols. And the distinction is very much like the distinction between a pipe and a picture of a pipe, or between Italy and a map of Italy. They're not the same thing. Logical shorthands, like we used in writing down phi, are used for logical analysis to clarify what's going on in a mathematical statement at the very symbolic level. There's a reason you don't see these symbols used in analysis textbooks to formalize mathematical proofs. You would see them used in a discussion of the formalism of mathematical statements, like in a logic course. You'd best avoid these symbols unless you really understand what you're doing with them. That means don't use them as a substitute for words and ordinary mathematical symbols when you're writing them in proofs in homework. It would be like putting quotes around everything you write. Now, at this moment, I am going to formally analyze some of the logic of our mathematical statements, so I will use the logical symbols here. I want to point out that one of the important and subtle things about what we're talking about here is the order in which our quantifiers appear. So this statement, the one that appears on top, says that every number is less than some other number. In other words, there's no largest number, or at least no largest element of whatever set I'm considering, depending on the context. True or false? Well, it does hold in the reals. By the way, when I say holds in R, that's the point at which I can make a meaningful semantic statement. The preceding list of symbols is just a formal list of symbols, so by itself it's not really true or false. Once I get to the point I say holds in R, then I've actually said something. If I interchange the two quantifiers, this says that there's an element that is bigger than every element. This property fails in the reals, and in the rationals, and in the integers. This statement says that there is an element less than every element. That also fails in the reals. In fact, it also fails in the natural numbers, and I hope you can see why. You might think, well, wait a minute. In the natural numbers, can I take x to be 1? Isn't that less than every element? Well, it's not less than itself. And when we say for all y, we're not saying that y is assumed to be different from x. There's no reason why it should be. Here, we are saying that every element has a multiplicative inverse. This fails in the reals and in most number systems. In fact, the ones we care about, the point is that you would have to exclude 0 for x to make this hold, which we can do. So here's a variation on that sentence. For all x, if x is not 0, then there exists a y, which is a multiplicative inverse. This says every non-zero element has a multiplicative inverse. Now this holds in the reals. It also holds in every field, but it does not hold in the natural numbers or in the integers. This says something very similar, and it turns out to be logically equivalent. This sentence really says the same thing. The point is that if x is 0, you can choose your y to be anything you want. And the final clause is valid. The thing in the parentheses is valid because the first part fails. So x not equals 0 doesn't hold when x is 0. So the implication as a whole is true when x is 0. You could pick y equal 1 if you want, or 0. Doesn't matter. You should think about why this really says the same thing as the previous line and why this is, in fact, a true statement, why it holds in the reals. So when you have something like the previous line, the quantifier buried inside, it's usually not too hard to move the quantifier out to the front and get the quantifier as far to the left as you can. Then we do need to be careful about the order of the quantifiers themselves. You cannot take that exists y and move it all the way to the front, but you can move it out past the other stuff most of the time. Here you can. So any two universal quantifiers commute with each other, and any two existential quantifiers commute with each other. But when you have a universal and an existential quantifier, they do not commute. This says that if you take any non-zero number and add 1 to it, you get something larger. This property holds in the reals. And you might be a little puzzled here because you don't really need x non-zero to get what you want. Nevertheless, the statement is true. And that's the point about having another example like this, just so you can understand something can be true and you can get a conclusion without even needing the hypothesis. So the arrow doesn't stand for any kind of a causal relationship. When you have an implication P implies Q, the only way that could be false is if P is true and Q is false. But that can't happen here, so our statement is universally true. Here is a way of saying that for every value of x, if x squared is less than 0, then 2 equals 1. And this is another example of what I just said. It has to hold in the reals. There's no way it could be false. The only way it could be false is if you had a counterexample in which x squared is less than 0 and 2 does not equal 1. Well, you cannot get an x for which x squared is less than 0 in the reals. Now that was mostly just practice with quantifiers, and now I want to look at some of the logical language that you may or may not have been exposed to in a calculus course, and which will certainly have a bearing in our analysis. And we don't need to do any more analysis to be able to talk about this. In fact, you should probably have seen this in a calculus course, but I'm betting most of you haven't. So let's talk about the definition of a limit. The limit is the most important and central concept in calculus. Unfortunately, one for which in our courses, our university, we just omit most of the time. We don't even open that section of the book. I've taught calculus here for over 30 years, and there have been times when we have taught the definition, but not currently. I'm not going to say everything about why we don't, but I will say that it is a lot to ask of students because of the following fact. The definition has these nested quantifiers. If you look at the formal representation of this statement of a limit, we've got a universal quantifier followed by an existential quantifier followed by a universal quantifier, and then inside that you've got an implication. So that's a tall order. So most students have difficulty getting beyond one quantifier and managing to hold that in their head. Now, on my previous slide, I tried to emphasize the subtleties that arise in dealing with two quantifiers. So if you ever get through a calculus without seeing what a limit actually is, I hope you'll sit down and dwell on this now, because it really makes calculus what it is. Let me just stare at the sentence that defines the limit and read it. If you have a function f from the reals to the reals, you say that the limit of f of x is infinity as x goes to infinity if the following statement holds. So this is a definition of that symbolic thing that I just wrote. It says, for all m, there exists an n such that f of x is bigger than m whenever x is bigger than n. It says that you can make the function as big as you want by just going far enough to the right on the graph. So there are several cases for talking about limits, and this is not maybe the first one you see in a calculus course, but in some sense it's simpler than the others. Understand if you want the function, for example, to be bigger than 10, that there is some point on the x-axis beyond which, to the right of, the function is bigger than 10. If you want the function to be bigger than 1,000, there is some point beyond which the function will be bigger than 1,000. If you want the function to be bigger than 1 billion, then there is a point beyond which the function is bigger than 1 billion, and so on. An important point here is infinity is not a number. We are using the lazy 8 symbol here in a purely symbolic way to stand for a statement which I've spelled out clearly. It has nothing to do with infinite. Everything is just numbers. No numbers are infinite. Nothing infinite here. In particular, there's nothing to do with aleph 0 or aleph 1 or anything from our earlier videos. Every number in the statement is just an ordinary real number. Everything is finite. Lazy 8 is just a shorthand whose purpose is to remind you. Now, another case for defining a limit is when x is moving to the right, but y is moving towards some number, hopefully. We say that the limit of f of x is L as x approaches infinity if the following statement holds. For every positive number epsilon, there exists a number n such that f of x is within epsilon of L whenever x is bigger than n. Just slightly more complicated. To paraphrase, you can guarantee the function getting within any required interval centered at L just by taking x to be large enough. How large? And that depends on how close you need the function to be within L. If you want the function to be within 0.1 of L, there will be some point in the horizontal direction. to the right of which that requirement holds. If you want the function to be within 3 decimal places of L, then there's some point, again, on the horizontal axis beyond which that will be true. If you want the function to agree to L within 10 decimal places, then there will be some point on the horizontal direction beyond which that is true, and so on. Now, this form of a limit is a little more complicated. This time, y is moving upwards while x is approaching some value a, but there's a complication that we're told to ignore whatever happens whenever x equals a. Whether or not the function is even defined at a and what its value might be there is immaterial, does not play any role in our discussion. In this case, we say that the limit of f of x is infinity as x approaches a if the following statement holds. For every number m, there exists a positive number delta such that f of x is bigger than m whenever x is within delta of a but not equal to a. You can make the function as large as you want just by forcing x to be sufficiently close to a but not equal to a. How close? That depends on how big you want the function to be. If you want the function to be bigger than 100, there's some small interval around a, not including a itself, such that the function there will be bigger than 100. If you want the function to be bigger than 1,000,000, then there is some small interval, probably smaller, around a, and again not including a itself, where the function values are bigger than 1,000,000, and so on. Finally, here is the first case for which the limits are usually defined in the section in a calculus book, but it takes actually more symbols and a little bit more thinking to get through the definition. We say that the limit of f of x is L as x approaches a if the following statement holds. For every positive epsilon, there exists a positive delta such that f of x is within epsilon of L whenever x is within delta of a but not equal to a. And you can force the function to be within any required accuracy of L just by requiring x to be within some small accuracy of a, and again not equal to a. If you want the function to be within 10 decimal places of L, there is a small interval around a, but not including a, in which the function value is within 10 decimal places of L. If you want 20 decimal places of accuracy for y, then you probably have to pick a much smaller interval for x. Now, because you probably didn't see the definition, you wouldn't have worked with any kind of limits like this in precise detail. So let me give you as an example a proof of a limit using the definitions, just to get a taste. So in a calculus class, you would have just had this as something to assume and use in computing limits. Here, we're actually going to prove the statement from the definition. So assume that f of x approaches 7 and g of x approaches 5 as x approaches 3. The goal is to show that the limit of f of x plus g of x is 12. Now let me give you a couple versions of the proof. In this first version, it'll be a little rough, and then the second version will clean it up. But if I just went straight to the cleaner version, it would be something like pulling rabbits out of a hat. So, the first run is strictly for motivational reasons. Let epsilon be positive. That's usually the first line in a proof in analysis. So, when in doubt, start off by saying let epsilon be positive. Let's write down what we know. There are two limits that we are given, and in each one, by definition, it says we can make a given function with an epsilon of some limit just by choosing x close enough to 3. How close? Well, for the first limit, we'll use a delta 1. For the second limit, we use a delta 2 because they would be different in general. So I use two different names. So f of x is within epsilon of 7 whenever x is within delta 1 of 3, and g of x is within epsilon of 5 whenever x is within delta 2 of 3, and not equal to 3 in each case. I want both f of x and g of x to be close to their respective limits. So how do I get both of these conditions to hold? Well, I take delta to be the minimum of delta 1 and delta 2. And now, if x is within delta of 3, then both the previous things will hold. From that, how do I get the conclusion, which is about f of x plus g of x? Why should that be close to 12? And here's where we use the triangle inequality. To split up, our distance is bounded by these two terms, both of which we have bounded separately. The bounds in each case are epsilon, and we add those and get twice epsilon. Now, that doesn't get the required thing to be less than epsilon. It gets less than twice epsilon, but of course, the goal was just to prove that something can be made as small as we want. And the point is still served, so any good analyst would say this is a proof. The result follows from this, but there's a little bit of cleaning up to do to make it easier for somebody to read. After all, isn't that the point of a proof, is to compel belief? So you want to make this as easy on the reader as possible. And if you're a student, you want to make it as easy on the grader as possible. Leave out any extraneous stuff. So it's a very useful exercise to clean up the previous proof, and whether or not the previous proof is strictly correct, that's not the entire point. Once again, let epsilon be positive. I will force both f of x and g of x to be within epsilon over 2 of their respective limits. Why epsilon over 2? That way the final bound will work out to be epsilon. Remember, we ended up multiplying by 2 at the end. So this way we get it to come out to be epsilon. And how close does x really need to be to 3? A single delta will do the trick. Why? Because if one delta is required for the first limit and another delta is required for the second limit, then, as we learned in our previous version, by taking the minimum of those two positive numbers, we get a new positive number delta that works for both of those. Now, when you've seen enough analysis proofs, you get used to this shorter way of writing it. So the required bound for f of x plus g of x is found by using the triangle inequality. The steps are as before, but now I'm cleaning it up. The proof is shorter and easier to read. One thing students overlook, a proof is supposed to be readable and clear. It's for a human to read, like maybe your grader. Its purpose is to convince a human being of the validity of a statement. So the clearer the better. Get to the point. No upside down A's, by the way. No backwards E's. No funky logic symbols. Just grammatically correct English sentences with all the right punctuation, spelling, everything, all the mathematical notation embedded correctly, and that's a proof.